been the integral from 2 to 3 or something like that. But you see, there is the possibility of talking about an integral that would go okay. An integral that would go off to infinity, or maybe even worse, minus infinity to infinity. And that's only part of the issue of what's proper and improper, because with the Riemann integral, for the number to be computable and be the same number every time you do it, your function must not be too badly discontinuous. You notice I put that in quotes because immediately that brings up the question, well, how badly is too badly? And so on. And so the books usually, for the first time through calculus, usually don't go into this very much. But for the Riemann integral to exist, in the sense that with the finite number limits, you can get a single value for the answer each time you would do the calculation. Your discontinuities have to be finite jump discontinuities. So, for example, if you think of absolute value of x over x, and you think of the picture, I don't know if I have any place I can draw a picture, but a picture of absolute value x over x as you go into 0 is a thing like this. Your graph is at -1 until you, as you approach 0 from the left, you don't have a value defined at 0, and then it jumps up to +1. So this is what you mean by a finite jump discontinuity. You can have a number of those and still be able to do your Riemann integral, because you can work your integral in pieces and put the answers together. The other kind of thing you can have, if I don't see a place I could really to draw the picture, but you can also call this kind of thing a finite jump discontinuity. If you notice at 1, what you get is 0 over 0. And if you were to factor the numerator, you'd have x minus 1 canceling this, and it would leave you x plus 1. So your graph is the line y equal x plus 1 with a hole in it at 1, where the form becomes 0 over 0. So a graph that's like a line with a hole in it, or a countable number of holes, that you can say is something where you can do the integral. Now I dropped the word countable on you, which is here. So countable means that however big your set is, if it's countable, you can tag everything in it. There is something, if you wanted to think of tagging whatever the members of the set would be, you can tag a member with 1, and another one with 2, and another one with 3, and there are no more members of the set to tag than there are counting numbers to use to tag. Now you might think, well, can anything be bigger than as many numbers as are 1, 2, 3, 4, so on? The answer is yes, if you think of an interval, like all the numbers between 0 and 1, thinking of all the decimal numbers that there can be, there are more of those than there are counting numbers available to use to tag them. This is the sort of thing that you don't really explore unless you major in mathematics and take upper division classes in advanced calculus, but it's actually so. So in order for us to be able to do the integral of Math 170, say, in the book that we're in, we must have a limited number of discontinuities, limited by no more than there are natural numbers to tag them. And they have to be either the whole in the graph type discontinuity or the jump like absolute value x over x in the picture. So that means that if you have vertical asymptotes, you see you have an infinite discontinuity, then you have an improper integral, and it is also improper if either what's here is minus infinity or what's up here is infinity, or both. And of course you can have something with the infinity symbol on one end or the other, or both, and vertical asymptotes as well. So there are the three types of improper integrals then. The type where you have the infinity symbol on one end or the other, or both, or the type with a vertical asymptote at some point in the domain of the integral. Could be at the start at C, at the other end at B, or somewhere in between. And then finally you can have something like this and vertical asymptotes. If you look in your book, they have this pretty well classified. I think this section is pretty well written, really. If you look in there, they have pictures of all these different situations that we would call improper integrals. So the way that we approach these things is we find the antiderivative and take the limit as appropriate at this end or that end or both ends as separately taken limits, and then see what you get in the limit with your antiderivative formula. And if you can get a finite number as your limit, then you can say that's the value, and you say the integral converges. And if your limit is infinite or just simply doesn't exist because what you have doesn't settle down on any number, like limit sine x as x goes to infinity, it isn't any specific number. It's just keeps switching between -1 and 1, and it never settles down. So you can have a limit fail to exist that way too. Okay, if your limit fails to exist, then you say the integral diverges, and you can't give a value. So I've written what I've said here. So when the limit exists, we call the integral convergent, and we say the integral converges to the limit value number. When the limit fails to exist, we call the integral divergent. Then, of course, we cannot give it a value. There also are comparison theorems and tests that you can use to establish that something is convergent, if it is, let's say. There's two ways you can go about this. There's the direct comparison test. It says suppose f and g are continuous on some interval from a, which we're thinking of as a positive number, to infinity, with the f less than or equal to the g, but positive value for all x from a onward. Then if the integral from a to infinity for the larger function converges, the integral, same a, starting point to infinity, of the smaller one converges. So this would establish convergence of this by comparison if your functions meet this condition that they're positive valued, and if the larger function is in an integral that converges. In the same way, if the smaller one, which I'm thinking of as the f, diverges, then the larger one diverges. If you have the comparison this way, if the integral of the g converges and you get a number value, you can also say that the value for this will be less than or equal to what this number is. You can't say that they're equal, and you don't know how much less, but it would be less than or equal anyway. Sometimes you have functions where this test doesn't work, but this one will. The last, or next to the last example over there at the end, is an application of this test right here. So suppose f and g are both greater than or equal to 0. They're both continuous for an interval beginning at a. And suppose the limit of the quotient is a number, positive number. When you say a number, you mean less than infinity, because infinity is not a real number, really. It's a limit symbol. So if you meet these conditions, your functions are not negative, they're continuous, you have a limit of the quotient, which is a number, then the two integrals behave alike. They both converge or both diverge. So if you could do a limit comparison test and your choice for g, say, is divergent, that would also prove that your function f is divergent. And if your g is convergent, meaning the integral of g, then the integral of f would be convergent. So let's look at some of the homework examples. Have some more recruits here to get the maple. You'll notice I've worked some of these out with the maple, and anybody else get in here and not get the function 1 over square root x has a vertical asymptote. So this one is this case, type 2. And so what you do is you use some letter, whatever you want. Say you could use b, is what I did. Think of the integral from b to 1 of your x to the minus half power. Do your antiderivative, nothing different about that. Add 1 and divide by the new exponent. so that's twice the square root of x, actually. And then take the limit with the antiderivative here, when you evaluated b, then take the limit as b approaches 0. You'd be approaching 0 from the right, you see, because you're square rooting, and you can't square root negative numbers. So you'd take your upper value, you'd have square root of, you'd have twice the square root of 1, and then minus, you take away twice the limit, square root of b, as b goes to 0 from the right. Again, it's from the right so that you can do the square roots. Well, the square root of 0 is 0, so you end up with just 2, and that's a number, so you say the original integral converges to 2, or that the integral is convergent. And I think that's, if I'm not mistaken, I think that's in the Maple. May not have. See if I did that one. If you look, let's see, I guess it's line 5. You notice Maple is everything that, each command that Maple has executed has a number on it. So I think it would be line 5 where I'm saying, with the capital I, to integrate 1 over square root x 0 to 1. So that prints the problem the way it looks in the book. And then you ask for the value, just the same as if it were a proper integral. And if you can get one, Maple will do it. And if you cannot get one, it'll say divergent. If you look through the handout, you'll see some of them say divergent, which would mean that there's no limit value to get. You'll get there. Meanwhile, look at problem 9, which is minus infinity to minus 2 of 2dx over x squared minus 1. If you sketch a graph, you notice that this, of course, this denominator factors. It's x minus 1 and x plus 1. And so there are 2 places where you're dividing by 0, at 1 and at minus 1. So there are 2 vertical asymptotes. So this can be an improper integral, either of the kind where you're going off to infinity at one end or the other, which is what it is, or the kind where you're crossing vertical asymptotes, or both, just depending on what limits you put on the integral. For the problem as it's given, they're only asking you to go up to minus 2, which would be about where I'm tapping the board. So it's improper just this kind, where the lower limit goes off to negative infinity. So it's a situation like this with the problem as stated. But notice that you could use the same graph for examples of the vertical asymptote type, or more than one vertical asymptote, or you could have the problem go off to negative infinity, cross a couple of asymptotes, and go off to positive infinity, depending on what you want to make out of it. So as it's given, you see what we have. So to do the antiderivative, you need, this is the kind where you need partial fractions. And you remember we studied partial fractions, was just last week, wasn't it? I think. And it's a couple of sections back anyway. So I would factor and say that my 2 over
x squared minus 1 will be a over x minus 1 plus b over x plus 1. And of course you can solve simultaneous equations, or you can do poles and residues, and I'm sure you know which I'm selling. And well, my father was a car dealer, so what can I be but a car salesman, right? So anyway, you take the pole here for A is 1, and the residue for A is 2 over x plus 1. You take the residue at the pole and you have 2 over 2, which is 1. So A is 1, and then for B, your pole 0 is minus 1, and your residue is 2 over x minus 1, and so you have 2 over minus 2, and you have minus 1. So what you want to do is the integral from b to 2 of this, which you do with the partial fractions, and then you take the limit as b goes to minus infinity. And you notice this one is log x minus 1, and this one is log x plus 1. And you should put on absolute values because these x's are are less than or equal to minus 2, so they're negatives. So you need the absolute values. And what I'd do is use my logarithm rules first. Before I try to take the limit, I'd say what I have is this log minus that log, so the difference of the logs is the log of the quotient. And the quotient of absolute values is the absolute value of the quotient, so you can simplify it quite a bit. And so now, you see at your upper limit, you can put in the minus 2, and remember you're taking absolute value. If you put minus 2 down there, you end up with a 1. You put it up here, and you have the minus 3. You have minus 3 over minus 1, so it's log 3, which I've done up here, you see. So at my upper limit, I have log 3, and at my lower limit, where I'm going to put in a b and go off to minus infinity, first of all, I have log of absolute value, b minus 1 over b plus 1. Okay, then I'm saying that the limit of the log of the absolute value is the log of the limit. Why? What is the property of the logarithm function so that the limit of the logarithm is the logarithm of the limit? Why can you do that? There's a one-word answer, and it's a property of the function here that you're taking the limit of. Yes, continuous. That's what continuous means, that the limit of the function is the function of the limit. And that's how we work limits, because the problems we work limits with are, generally speaking, continuous functions. So that's true with the trig. Limit of the sine is the sine of the limit. The log, the exponential, the square root. And now I have limit of the absolute value of the fraction. And here, and now I want to say that the limit of the absolute value is the absolute value, see, of the limit. Why? Same thing. The absolute value is a continuous function. So you're using continuity property twice to get from limit across the log to here, and then from limit across the absolute value side to here. So you end up log absolute value of the limit for this fraction. Okay, so finally, what's the limit of this fraction? What's this limit inside the absolute values? Well, you can use L'Hopital's rule, or you can do as you would have in Math 143 or 147, where they tell you if you're talking a limit of a quotient of polynomials as your variable goes to infinity, you divide top and bottom by the highest power in the denominator. You see you'd have 1 minus 1 over b, 1 plus 1 over b. And then your 1 over b would be 0 in the limit as you go to infinity, so you'd have 1 over 1. And that's what you'd get if you use L'Hopital's rule. If you think of b as a variable and do your derivatives, you'd have 1 here and 1 there. So you have log of 1, which is 0. So you have log 3 minus log of 1. So you have log 3. So your answer, finally, for problem 9 ought to be log 3. Now let's see what Maple thinks it is. I think it's there. It might be, I didn't do this one with the Maple, but. Oh, yes, here it is. It's on the back of the first sheet of paper. It's number 15. I use t instead of x, but integral of 2 over t squared minus 1. And I guess that instead of minus infinity to minus 2, I went 2 to infinity, but you see it's essentially the same problem. It's the area over here under this tail, and the thing is symmetric. Yeah.
Professor Maloof, that's 9 and 10.
Oh, okay, yes. If you go back on the first sheet, on the front side, 9 is where I have the problem. The problem is this one. And minus infinity to minus 2. And then value is 10, which is log 3. And then if you turn the page, you notice where I was with 15 and 16. You have basically the same thing. As I was starting to say, instead of under this tail, you're over here under this tail. So you should expect it would be the same answer because it's the same area. Okay, take a look at 20. Any questions so far before we look at 20? This isn't really that hard to do, these improper integrals, but they are something that you haven't seen until now, unless you're taking the class over, of course. Then you'll see it. And so if you look at 20, we have 16 arctangent x over x squared plus 1, 0 to infinity. So this is improper because of the infinity, at least. I don't think that, well, you wouldn't have any vertical asymptotes in there because your denominator cannot be 0. And your arctangent is a graph that goes sideways. Tangent has vertical asymptotes, but this is arctangent. And if you remember, the curve goes wire here. Mathematical models. There's nothing like them. So if this is your vertical axis, then your arctangent graph is a thing like this, like the wire, and it has an asymptote down here that's horizontal at minus pi over 2. Let's see, I guess it goes this way, actually. It has one that's horizontal up here at pi over 2 and over here at minus pi over 2. So it doesn't have vertical asymptotes. So what you have is a U substitution problem, because if your U is arctangent, then, and you can factor the 16 out in front and get it out of the way. It's just there to confuse the students. The derivative of arctangent x is 1 over x squared plus 1 squared. So if this is the u, then the dx over x squared plus 1 squared is the du. So then you change the limits to limits on u, and then if u is arctangent and x is 0, the u is 0. If u is arctangent and x is infinity, then the u is pi over 2. So when you do that, you're actually not working with an improper integral anymore, except that you do your integration and you have the 16u squared over 2 and put in your limits. You come out with an answer, so you'd say the integral converges. And this one is in the maple, I'm quite sure. See if I can find. This is on the back of the first sheet of paper. Number 17, I've defined my function as 16 arctangent x over x squared plus 1. Notice with maple, with the inverse trig functions, you spell it out, arctan or arcsine or whatever. And you can draw the graph, which I did, and you see it doesn't have any vertical asymptote, really. And then I set up the integral, that's number 18, and then ask for the value, and that's the 2 pi square. Well, I think all's ashore that's coming ashore. And you see, the reason that this is improper, you don't see an infinity symbol, and it isn't obvious that you have an asymptote, but the problem is the x log x, because log of 0, well, your limit of the logarithm as x approaches 0 from the right is negative infinity, or the log graph has a vertical asymptote at 0. So the question is what you get with a form that looks like infinity times nothing, you see. Your limit as x goes to 0 of x is 0, and your limit for the log is minus infinity. So this is the indeterminate form, infinity times nothing. If you go back to the chapter in 170 where we had
L'Hopital's rule and indeterminate forms. I can't tell you exactly what section, but it's there. They list what they call indeterminate forms, like infinity over infinity and 0 over 0, and infinity times nothing, and 0 to the infinity power, and 1 to the infinity power, and infinity to the 0 power. There's 7 of them altogether, I think. So this is actually an indeterminate form at that limit. So that's why it's in the homework. And if you look at the graph, you can ask your graphing calculator to draw the graph, or Maple. You get a graph that looks like this, and it would appear that your limit is actually 0 for x log x. Well, you can work the problem out because we can integrate it by parts. If you remember the section, I guess it was the very start of chapter 8, it would be section 8.2 if you're in the newest edition of the book. We had integration by parts, and I had that rule that gave the preference order for what to call u, and then what was left is what you'd call dv. Remember, it was L-I-A-T-E. So logarithm, if you have a log factor, that's always your first choice for u. And then the I was inverse trig, and the A was algebraic, and T was trig. So use log x, and this is du. Then, if you're going to try and integrate this, the dv is x dx, and you get the v. So your integral is of u dv is uv between your limits, and then this is actually where you get into the improper integral again, you see, because what's your limit as x approaches 0 of x squared log x? Well, that's this improper integral form, you see. So that's why it's in this section as a homework problem. Minus the integral of v du. Here's the v, and there's the du. You notice this is an integral you can do with no trouble. The x cancels one of those, and you have the integral of 1/2 x dx. And so then what you have is at 1, you have 1/2, 1 square, which is 1, log of 1, which is 0. Then at the lower limit, you have minus 1/2. The limit of what I did is I factored the x here, that x, and then x log x. And then you can look at the x log x graph and see that that limit is 0. So you have a limit of x as x goes to 0 times the limit of x log x as x goes to 0, which you can see is 0. So, and then over here you have this part, the integral here. You cancel the x and then integrate, you have x squared over 2. So what you end up with then is the minus 1/4 out of this. Because for this first part, you have 0 at both ends. It's 0 at 1 because log 1 is 0, and it's 0 at 0 because you have this limit as x goes to 0 of x and x log x, and that's 0 times 0. So that's all gone, and your value is just what you get out of this. And you notice the integral is negative. Your curve is down below the x-axis. If you wanted the area, you have to go top minus bottom, which is the same thing as if you took the absolute value here. The area is an integral, but an integral is not necessarily an area. For it to be an area, it has to be set up top curve minus bottom curve, or right curve, right hand minus left hand to be positive. Okay, so just a second, I have another customer here. So then, if you look at 37, the problems 37 through 40 involve the comparison theorems. And it isn't clear at the start with 37 or 38, which is basically something you work the same way as 37, how this comparison is going to go. You have to do some substitutions. What we're doing here first is playing games like the section 4, I guess it is, in chapter 8 in the new edition of the book, where we had those trigonometric substitutions to replace either a sum or difference of squares by the square of a single trig function, usually because there was a square root sign, and then we could do the square root of the square and get rid of the square root. And then the price we paid was we had to work with the trig functions, if you remember doing that a couple weeks ago. Well, this is similar. The game here first is a substitution to make this a single letter under the square root. And we're going to end up calling the single letter that replaces pi minus t x, and then we're going to be comparing the function 1 over square root x with something else for convergence or divergence. And if you remember, we've already studied the nature of the integral of 1 over square root x back here, and found that the thing, if 0 is one end here, we found that the thing is convergent, even though we have a vertical asymptote. So we're going to be doing this same kind of thing here with this substitution. We call this x, this pi minus t. So our gain is we get to put the single letter under the square root, and then we use trig identities here. If x is pi minus t, t is pi minus x, and so then we're going to have, at some point, the sign of pi minus x, you see, in a trig identity when we get there. So that's our game plan. We also have to change the limits, which are on t, to new limits on x. Notice that if x is pi minus t, so that t is pi minus x, then dt is minus dx. Our limits on x then, when t is 0 and x is pi minus t, x becomes pi. So our new lower limit is pi. Our upper limit
t is pi, and x is pi minus t, then x is 0. So our new limits are pi to 0. In here we have sine pi minus x for just a minute until we use our trig identity. For the dt, we have minus dx, and for the big gain here, we now just have the single letter under there. So as I said, and it's like section 4, where we're converting this to a single variable. So then what you can do is reverse the order of your limits and use the minus sign here to pay for it. So now you have 0 to pi, sine pi minus x over square root x. Now use your trig identity, and you get to simplify this. So the sign of the difference is the sine of the left hand, cosine of the right hand, minus, if that's a minus. If this were a plus, this is a plus. Cosine of the left hand number, or entry, or variable, whatever it is, sine of the right hand. Okay, and sine of pi is 0, so that's gone. And cosine is minus 1, and the two minuses make a plus. So this is the same thing as that. All that says is that if you think of the sine graph, if you move over a distance of pi, you have the same value again. And so you have sine x over square root x. Okay, now what we proved in number 3 over there would show that your integral 0 to pi of dx over square root x would be 2 times the square root at your upper limit. And you know that your sine is between 0 and 1, and so if you compare the function f, 1 over square root x, with the function g, which is sine over square root, that's less than or equal to f, because sine is less than or equal to 1. So if f converges, g converges, which is this integral, which is this one. And the value to which it converges is less than or equal to what would be here. See, with this one, again, if you just look back at what we did, it's just like this, except here I have a 1 and there I have a pi. So what did we do again? We integrate this, so we have twice the square root, you see, for our antiderivative, and then we take our limits be, here it was 1, but now it would be pi. So if you put a pi there on our work here, it would be just what's over at that problem. And so you'd have twice the square root of pi minus twice the limit, which is 0. So you'd have 2 times square root of pi. And that's what I have here. And then I'm saying that this converges, and what I have with a sine over square root x is less than or equal, but still positive. And so because this converges, that does. That's your comparison test. So that's somewhat involved, but it goes through. Take a look at 39, where we're going 0 to log 2. And you see you have x to the minus 2, or it's divided by x squared, like this. So that's why it's improper, because at 0, you're dividing by 0 here with this factor. So if you do a substitution, if 1 over x is y, then your dy is what I get here. So finally, what I have is that the 1 over x squared dx is minus dy. So that and that go together to minus dy. This becomes e to the minus y minus dy. And then you need to change your limits, because you've changed your variable from x to y. So x is 0 and y is 1 over x, says y becomes infinite. So you're going to have an infinite limit now with the new variable. That makes it improper. And then x is log 2, your y will be 1 over log 2. So first it was infinity to 1 over log 2, e to the minus y minus dy, and I use this minus sign to switch the order and write it like this. Now the integral, as far as doing the antiderivative here, is easy enough, and then I put in my 1 over log 2 on the bottom and a b that's going to go to infinity in a limit. And I grind through this, and I end up with this answer, which I think Maple has. I think 39 is there. And, may have to go through some pages, but so number 39 is on the back side of the third sheet of paper, of your 4 sheets of paper. And if you notice number 45, line 45 is integrating 0 to log 2 e to the minus 1 over x squared. And 46 is the Maple answer. So here is an example. This is an example that's in your book, actually, that is designed to show what you would do with the limit comparison test. And that's a test that's worth understanding how to use. So if you look at this integral, the question is, does it converge or does it diverge? And you see, you could think of what you have inside the integral as your function f of x, and you could think of a g of x, which is just 1 over x, and those then are functions you could compare. So first of all, if you look at your graph of e to the minus x, see it goes like that. Then if you put a minus on it, you reflect across the x-axis. So minus e to the minus x is this curve. Then if you add a 1 to a curve, what do? You raise it by that much. This is the kind of thing that they go through in Math 143 or 147, where you change the sign on the formula, what do you do with the curve, and so on. So it's the sort of thing where you're now in a Math 143 class, you see. And so we start out with e to the minus x. Then if we want to put a minus in front, we flip it across the x-axis. But other than that, you preserve the shape. Then if you're going to add a 1, you raise it 1. But other than that, you preserve the shape. Okay, so what we have is that 1 minus e to the minus x, which is our numerator here, is something that starts out at 0 when x is 0. E to the 0 is 1, and 1 minus 1 is 0. And it looks like this, and it stays below the line y equals 1, which is its horizontal asymptote. Okay, so what I'm proving is the numerator is less than or equal to 1, so therefore this function is less than or equal to that one. So I can compare this function to that, certainly. The problem with the direct comparison, though, is that the integral of 1 over x, as you go off to infinity, is the logarithm. And see, if you look here, as an improper integral, your integral 1 over x is divergent. And the fact then that the g, the original, is less than or equal to a divergent integral doesn't prove anything. If your 1 over x were convergent, then this being less than or equal to that, you'd prove this is convergent. But when this is divergent, which is what it is, you can see right here, you haven't proved anything. So you can't just use the first of the two comparison theorems. In other words, you cannot use this one because it has to be that the bigger function converges to prove that the smaller one does. And it doesn't, it diverges. But what I'm trying to get at is I can say that the two functions approach a limit, and if that limit is a positive number but finite, then I can say the two integrals behave alike, and I have proved that the one that I'm calling f with the 1 over x is divergent. So I'll prove this diverges provided I can show you that the limit of the quotient is a finite number. And that's not that hard to do. Your two functions here, this one and that one, are, we've proved that the f is less than or equal to the g. We've proved that they are continuous and that they are not negative, because your g, your numerator for this function f is greater than or equal to 0, and the x by which you're dividing is positive. So positive over positive is positive. Well, if you do your limit of your quotient, you see you invert and multiply here, and the x's cancel, so you have this limit, and you can see that's 1, because if you have a graph with a horizontal asymptote, the limit of your function that defines your graph is always the y value for the horizontal asymptote as x goes to infinity. So this quotient does approach a limit, which in fact is 1. Doesn't really matter whether it's 1 or 2 or a half, but it's a positive number. It is 1. So the integrals behave alike, And we know this integral, which is my integral of what I've called G here, is divergent. So the other one is. So that's an example of the kind of thing you can do with a proof type approach. Okay, last example for the week. This is a famous problem in calculus, and the thing is called Gabriel's horn, thinking of like that, a long trumpet sort of thing. And your graph here is 1 over x from 1 off to infinity. So this is an improper integral of the type where your limit is infinite if you're talking about either the volume of the figure that you form by rotating this curve around the x-axis, or if you are thinking of the surface area of the figure that you form if you rotate this curve, which is a figure that would look like the traditional trumpet type horn of the original kind that didn't have the valves. It was just like that sort of thing. And so imagine then that you form the solid of revolution revolving 1 over x around the x-axis. So your surface area would be 2 pi times the integral, your radius, which would be the 1 over x, and your differential arc length. Remember, we did those in chapter 6, I guess. And the volume would be pi if you were using the disk method, radius, which is 1 over x squared, integrated 1 to infinity. So if you do the volume first, you notice it's an improper integral, and write 1 over x as x squared as x to the minus 2. Remember, what you do is you add 1 and divide by the new exponent. So you have x to the minus 1 divided by minus 1. So that's why the minus sign. And the x to the minus 1 is 1 over x. And you take that limit as b goes to infinity, and your limit of 1 over b is 0, and at your lower limit you put in the 1, and so you have minus pi, 0 minus 1, so it's pi. So this does have a finite volume, okay? But if you look at your arc length, remember your differential arc length is the square root of 1 plus the derivative squared dx of your upper curve that you're rotating to form the surface. So your derivative of x to the minus 1 is minus 1 x to the minus 2. So 1 plus the derivative squared. So that's 1 plus, because you're squaring, 1 over x squared squared, so x fourth. So your surface area is 2 pi, your radius, 1 over x, your differential arc length. And this is, under the square root, this is more than 1, because it's 1 plus something that's never negative. So this is bigger than 2 pi times what you have with just this factor, because this, what I am about to enclose in a blue circle, is greater than 1. Okay, So your surface area is more than this. But this integral is your logarithm. That's this same integral again. Here it is, right there. So you read down here, this diverges. So you see you can fill the container, but you can't paint the outside, is the paradox. This is a famous paradox in mathematics, you see. That there's enough paint to fill the can, but not enough paint to paint the surface. Doesn't make much sense, does it? Okay, so it's certainly what the math says, but you see our model on using calculus for surface area breaks down if you get to something that's an infinite surface like this. Our model of chapter 6 for volume and surface area and arc length is one thing if you're talking proper integrals with a to b, but if you go to an infinite limit like this with an improper integral, then these models can break down in this way. It's a little bit like some of the things you get into with gravity and black holes and space warp and all that sort of thing, but some things get a little shady, let's say. But this is a famous classic problem in calculus, so I thought you should at least see it and you can think about it. Well, what we will start with next week is differential equations. We don't do anything like the Math 333 course in differential equations, but there is some in chapter 7, and then there's more in chapter 9, and so we'll be working with those things next. So hopefully I either